All right. Well, thank you all for joining. I am very happy to introduce Neeloy. So as many of you know, Neeloy started as an undergraduate here, and he started working in my lab, I think, in your junior year, correct? Right? And then went on to do his senior thesis, and we loved him so much we wouldn't let him leave here. One of my favorite things about Neeloy is that even from the get-go, he was so mature and just good at what he does that when graduate students would come into our lab, they thought Neeloy was already a graduate student even when he was barely starting in the lab. So he's very mature. Unfortunately, that means I probably had very little to do with it, so we can probably thank his parents here in the third row. But one of my favorite memories, I guess, of Neeloy, beyond just everyone assuming that he's way advanced, is for his undergraduate thesis. He initially started working on multi-agent reinforcement learning, and he wrote this just kind of survey literature review. And I loved it so much because it was so good and so thorough that every time some student came to me saying they wanted to do multi-agent reinforcement, I was like, oh, go talk to Neeloy and get this survey. And I loved it because it was so good, no one wanted to keep doing it. So it was like my way to stop people from getting into this area because it was so complete. But anyways, with that, I'm happy to turn the time over to Neeloy.
Yeah. Thank you so much, Katie, for the sweet words. Yeah, I've had a lot of fond memories here, and I'm really excited to discuss my work today on human-robot teams under failures, adaptive solutions to varying capabilities and roles. I'd just like to confirm that people in the audience can hear me, okay? Okay, I think I see head nods.
Zoom as well.
Okay.
We can hear fine in Zoom as well, yeah.
Yes, okay. Okay, so I envision a future where humans are seamlessly assisted by embodied or real-world agents. And what that means is developing intuitive communications methods to enable these different agents to talk to one another, developing these agents such that they're intelligent and creative while being guided by safety standards, and also to align the uncertainty between these different agents in your multi-agent world. And we can visualize a human-robot team spectrum, where on one end of the spectrum, we have robots that are great at performing repetitive tasks, or robot navigation, or assembly. And on the other end of the spectrum, we have humans who are very creative, and they can take decisions based on their prior domain experience in the world. In the middle, we have human-robot teams. These are systems that are collaborative manufacturing, or teleoperation, or surgical robots. These take the pros and cons from both sides of your spectrum. And we can represent each of these different scenarios with a graph where we have multiple robots collaborating with multiple humans towards a common goal in one environment. And there may or may not be other agents performing their own tasks towards their own goals in the same environment. And during today's talk, we'll be focusing on instances where there's one human collaborating with one robot. We can remove different edges from this graph to represent different scenarios. For example, an instruction following scenario, a case where there are no other agents in your world, or instances where there is no direct communication between your human and your robot. The issue is different failures could arise at any point during this pipeline. For example, there could be communication interrupted between the human and the robot. There could be instances where your robot makes poor decisions, or there could be other failures with the other agents. And what I argue is that we need to design anomaly-aware human-robot teams. These are systems that are designed such that are aware of potential failures throughout the entire development and deployment process of these systems. And to that end, during my PhD, I've worked on deploying planners in safety-critical scenarios like robot crowd navigation and autonomous driving. I've designed proactive characterization methods to understand where these planners might fail prior to deployment. I've also designed algorithms to understand where these models might encounter anomalies in real time in the real world. And finally, based on our understanding of where these pipelines might fail, how do we react to them, either through fine-tuning our policy or maybe switching control over to a human teleoperator. And as we can see, this is a cycle where we can continuously improve our pipeline. And during today's work, I'll be focusing on 4 of these projects that really tackle the failures between the robot and the human, the robot and the environment, and the robot and the other agents. Specifically, we'll be seeing how we can tackle varying levels of robot capability and varying levels of human domain experience required to understand where these failures arise from. So we'll begin by looking at low-level teleoperation that requires a lot of domain experience from your human teleoperator. Switching to this higher-level instruction following scenario, where we might use modules to understand where the failures might arise from. And finally, diving deeper into how people are deploying large foundation models as planners, which might be black box systems that are really difficult to understand where your root cause failures arise from. And during this presentation, we'll be discovering how can we design tools that enable for effective failure intervention across these varying levels of human capabilities, human experience and robot capabilities. So again, we'll be tackling low-level teleoperation, high-level instruction following, and finally stress testing of these large black box systems, where the role of your human will really shift throughout this entire design process. So we'll begin by looking at how we can assist humans to control robots and find these failure cases. We'll then present a taxonomy of different large language model failures that might arise. And finally, we'll be seeing how we can enable engineers to proactively characterize their models prior to deployment. So this is an agenda for today's talk, where you'll see the bulk of today's presentation will be on my work since my prelim exam on how we can stress test models proactively. But we'll begin by seeing how we can assist humans to control robots and identify the root causes of these failure modes. So failures are inevitable, of course, in your pipeline. One solution is to rely upon teleoperation, where a human might be controlling your robot from a far distance by relying on a video feed, for example. Teleoperation is used in the agriculture domain to monitor the status of your crops, monitor the status of your robots, as well as whenever your robot might fail or crash, you can rely on a teleoperator to potentially move you out of that failure mode. Now, there's several challenges with current under-canopy teleoperation methods due to transmission delays from the field to your computer. There could be regions in your crop that have signal fades or dead zones where there's no communication at all, and there's also occlusions caused by your crops. And what we really aim to do is to compensate for these dropped frames. So how we can sort of formalize this is we have images and poses that are being sent from your robot, and we have some prior domain knowledge of what your calibrated camera intrinsics are. These frames might be dropped or delayed as they're sent to a remote computer. And what we aim to do is generate these new images that align in real time with what the robot is actually seeing, such that our human can take updated control actions and send them back over to our robot. And for today's work, we'll be focusing on how we can compensate for delayed frames, currently ignoring the issue of this delayed control. So what we really aim to do is to build up a 3D representation of your world, given images that we receive on the computer side. And one way to do this is by relying on a depth sensor. However, sending depth images from the field is very expensive under bandwidth constraints. So this is where we can rely upon a depth estimation model, which will estimate how far away pixels are from your camera. And we train this model relying on ground truth data we can collect from the real world across different growth stages and across different weather patterns in real crops. We choose to fine-tune existing large foundation depth estimation models using root scale invariant loss to really improve these depth estimation models to the agricultural domain. And what we find is, given any conditioning frame we receive on our computer side, we can estimate what the depth is, we can build a 3D world and move our camera forward in time such that we can render what the future images might look like. As you can see, as we get into later and later growth stages, there's a lot more occlusions caused by your crops that are now becoming unoccluded, and we need to really in-paint these regions before we showcase them to the user. This is where we rely upon an in-painting model. We choose to train this in-painting model conditioned on our original image and our projected rendering, and we train this using reconstruction loss, again relying on our large data set collected out in the real field. And what we find is by combining this projection process with our in-painting model, across different growth stages and across different time delays, our approach produces the highest quality and most accurate renderings compared to the ground truth frames in the real field. And we can visualize what this looks like on a real ROS bag here, where the top left video feed is what the robot might be seeing, and the top right is what a user might see without our compensation method, and the bottom left is what's shown with our algorithm. And this is much smoother than your low FPS feed, but there's still jumps in your video feed generated due to poor estimations in your post-prediction model. And this is to be expected in these sorts of rough terrain agricultural domains, and that's really a limitation of the current post-prediction approaches. So teleoperation really enables domain experts who have knowledge about how your robot will react to your control action and in your environment. But what we really want to do is to enable non-experts to collaborate with your system. And this is where natural language provides this intuitive interface to communicate with your robot. And we specifically explored this task of instruction following within the Alexa Arena Embodied AI Simulator, which provides this gamified interface to interact with our robots and collaborate with them on different missions, but by providing instructions to the robot. And interestingly, this simulator, unlike other simulators you might be familiar with, abstracts away low-level navigation, enabling us to focus on this core task of translating high-level instructions to sequences of ungrounded actions to take in your environment. So here's an example of my collaborator, Hao Miao, working with our robot in the simulator. He can ask different instructions, for example.
Alexa, pick up the soda can.
And
we're going to make a great team.
And he can also ask more complex instructions, for example.
Go to the blue shelf.
And our robot will respond.
Okay, I'll look around.
And as we can see, this mission will continue to evolve as our Hao Miao gives different instructions to it. And I won't play the rest of this video. But existing instruction following methods really boil down into two different types. We have modular approaches that rely on separate modules for converting speech to text, object detection, and more. These approaches achieve state-of-the-art metrics within different benchmarks, but they have limited generalizability due to sorts of limitations like requiring hand-engineered task templates. And on the other end of the spectrum, we have end-to-end systems that rely upon these large multimodal systems that will take in multimodal data like speech, images, and text and directly convert them into grounded actual actions in your environment. These approaches are more data-driven. They require less engineering, and they're less prone to these compounding errors, but they require this expensive process of data collection, and they're less interpretable on the deeper level. Really, where we fit into this pipeline is that our approach is modular, where one of our modules is converting these text instructions to sequences of actions to take in your environment, no longer requiring these task templates. And simultaneously, by relying on this modularity, we are able to fine-tune individual modules in our pipeline separately quicker without having to collect this multimodal data set. And this was critical during this competition because we were receiving user feedback on a daily basis, and we need to improve our policy very efficiently. Finally, what I really want to showcase during this presentation here today is that modularity assists us with isolating the root cause failures of different failure modes in our pipeline. So as we go from this low-level teleoperation scenario to this higher capability instruction following environment, we'll be seeing how modularity enables us to identify what these root cause failure modes are for us as engineers to fix them based on user feedback. This is where I introduce Beast, which is building an embodied action prediction system with trajectory data. It consists of this instruction to action translation transformer model, as well as this action execution pipeline. And for the sake of time, I won't be going in depth into either of these systems, but I'd be happy to discuss them during any questions. We compare this modular approach against different ablations and baselines. So for example, we vary the action model's access to clarifying question data as well as prior instructions given to your model. And we also evaluate how your policy does with and without ground truth object detections from your simulator. And we compare against different baselines like other modular approaches, as well as an end-to-end vision language model. And this table here showcases what is our ratio of missions that we actually succeed in across different robots and across different mission types. The first thing I want to point out here is that when provided ground truth vision, our robot with this history data has the highest success rate, outperforming all other robots, including our end-to-end vision language models. However, we see that using this ground truth vision data drastically improves our success rate, obviously meaning that our object detector has limitations. And again, I'll be talking about how our modularity enables us to find these root cause failure modes. Interestingly, we found that including clarifying questions actually decreased our bot success rate. Again, by performing root cause analysis, we found that the grounding module was actually not handling these sorts of clarifying question data, and it was actually confusing our action prediction system that led to poorly executed actions in your world. And we see that our vanilla robot alone outperforms most of these other approaches, but the end-to-end vision language model with its QA data produces these better grounded segmentation masks, leading to these fewer failure modes. And so you go into the actual modularity, how it helps us to identify these root cause failure modes. This is one example where we identified by looking at the closed loop metrics, our policy has a high navigation time. It requires several steps to complete a mission. We found that, for example, looking at our object detector, there are several instances of objects that are difficult to find. This leads us to either fine-tune our object detector to these objects or improve our action execution pipeline to reach more favorable states where we can identify these objects better. And really, this is just one example of a root cause failure analysis we can perform. What I really want you to take away from this section of the talk is that modularity enables us to identify these bottlenecks in our pipeline. And this rule-based grounding worked well for this sort of abstracted deployment where we didn't need to care about low-level control or navigation, but it's difficult to scale, limiting its generalizability. And this Alexa Arena simulator was interesting, and it was helpful for us to evaluate how real humans would interact with a robot in this simulation, but really higher fidelity simulators are more favorable before deploying in the real world. And I'll discuss that later on in this talk. And feel free to ask any questions along the way if there are happen to be. Yeah. And this brings me to the next section of the talk where we can identify and build a taxonomy of different hallucinations that can arise by relying on large black box foundation model planners. So we saw how these classical planners and these modular-based approaches have some limited generalizability, and people say that they lack some sort of common sense needed in new unseen scenarios. This is where people believe that large vision language model planners might be more convenient and useful because they're trained on such a large data set. So people are deploying them in high-level decision-making, path planning, trajectory prediction, answering questions about their scene, and low-level control. The issue is relying with these sorts of large models is that they can hallucinate. For example, they might incorrectly detect objects in your scene, they might embellish details and add additional context that was never asked of it. They might provide incoherent reasoning for why an action was taken, or they might predict infeasible actions and plans that are actually not feasible to be deployed in the real world. So how do these different hallucinations come about? They might arise from different sources like biases in your training data, a malicious actor providing adversarial prompts, or you might be conditioned on out-of-date information, or the weights that you've trained might be poor for your task at hand. Or the decoding algorithm might result in compounding errors in your generation. And by looking at 4 different domains where these large language model planners are being deployed, we develop this flexible definition for what hallucinations are. We say that a hallucination is a generated output from your policy that conflicts with hard constraints or deviates from desired behavior or is completely irrelevant to your task at hand, but could be deemed semantically plausible. Really, this definition requires 3 different things. We need a generated output from your policy. We need a list of hard constraints, a desired behavior in the form of soft constraints or a reward function or a cost function, as well as a set of relevant topics that our policy shouldn't stray from. And finally, we need metrics for measuring compliance, desirability, relevancy, and plausibility. And we'll be seeing later in just a little bit how actually defining hallucinations in this formal way, we can actually provide generalized guidelines for how developers should create their own hallucination intervention algorithms. Existing hallucination intervention algorithms break down into 3 different types. We have white box approaches that require access to internal model representations. And these are not very flexible. They can't be deployed to closed source models like GPT. There's other approaches like conformal prediction that require access to the output token probabilities. And the most flexible of them all are these black box approaches that only require access to generated outputs. And these approaches might check for consistency over multiple samples from your model, or they might look for they might use a proxy model as a representation for your closed source model. And these approaches are much more flexible. And just a quick peek into our survey, we studied 40 different hallucination intervention algorithms and looked at the common metrics people were actually designing for these different domains, including question answering, image captioning, image generation, planning, and control for each of the different characteristic types, including compliance, desirability, relevancy, and plausibility. And by providing these different metric types, we provide generalized guidelines for how engineers should develop their own hallucination intervention types. So the main takeaways from this section of our talk is that we've identified several instances of where these failure modes really arise from. And we provide these flexible definitions for what hallucinations are. And we present these general guidelines for actually designing these intervention algorithms. And what I really argue is that researchers should really analyze their model tendencies, especially before deployment in safety critical environments like robot navigation or autonomous driving. Rather than building benchmarks solely on question answering tasks, people should really be evaluating them also in planning contexts. And finally, I suggest people develop these different sorts of algorithms that are applicable to black box closed source models. And that leads me to me developing my own stress testing algorithm for characterizing these sorts of policies. So we saw how large vision language models are acting as planners in different areas like autonomous driving, robotics, and other domains. This is an example of AlphaMail. This is a vision language action model policy developed by NVIDIA that takes in prior image frames as well as a conditioned navigation instruction from a human user, and it generates what is your predicted trajectory for the ego vehicle and reasoning for why that trajectory was generated. So in this video you see on the right-hand side here, this is a case where our vehicle overtook a stalled school bus before coming to a stop at a red light. And what I really want to note here is that this video is not taken in the real world. This is a simulation. This was optimized through optimizing Gaussian splats. And it really enables us to produce a higher fidelity simulator compared to the Alexa Arena environment we were able to characterize models in earlier. The reason this is important is so that we can actually understand our model characteristics prior to deployment in the real world. And really, when we're trying to characterize our policy before deployment, we can define different perturbation dimensions that enable us to understand how robust our policy is under these realistic perturbations. So the 4 key perturbations I define include sensor perturbations. These might be caused by a distribution shift between your training and test time evaluations, where maybe it's a change in your camera. There could be scenario perturbations caused by changing your map or the environment, including weather patterns. There could be changes in your trajectories of the other agents in your world. And there could be other issues by changing and augmenting your prompt, maybe conditioned on a conservative prompt versus an aggressive one. And what we aim to do is to characterize the robustness of a policy under each of these 4 axes, where one model may be highly robust to trajectory and scenario perturbations, whereas another policy might be highly robust to sensor and prompt-basing perturbations. What we really aim to do is to characterize our black box systems uniquely along each of these 4 axes. And for today's talk, I'll be focusing on how we can characterize along the sensor, scenario, and prompt-basing perturbation axes. The trajectory perturbation characterization is currently under work with my collaborator, Yi Xiaofeng. So these are some examples of how a policy can how AlphaMail reacts to just a little bit of posed perturbations. We find that here, our vehicle actually runs a stop sign, and it actually chooses to drive up onto a sidewalk. I'm sorry if it's kind of hard to see in the room. The lighting's a little bit bad, maybe. Thanks, Katie.
Please leave switches in the on position. Okay.
Oh, maybe one of those. Maybe it's okay. We can just go on then.
Yeah, it's really good on Zoom.
Yeah, okay.
It looks great.
Great on Zoom.
I'm tempted.
Yeah, I think it's okay.
Yeah.
On the right-hand side, this is another example where a policy is fed just a little bit of post perturbations, and it leads to it actually aggressively merging right behind another vehicle in the left lane before quickly realizing this car is moving too slow for my own preference. I'm going to merge back into my original lane. We can also apply some aggressive driving prompts. So this video is especially difficult to see, I believe, but essentially there's a semi-truck right here, and our vehicle is going to merge and overtake this vehicle on the right-hand side. This aggressive prompt actually leads to overtaking utilizing a lane that's about to end. So it's extremely unsafe. I want to note here that there's actually a lot of artifacts in the rendering, in the Gaussian splat here. This is caused to reaching new states that were not previously optimized during the Gaussian splat optimization process. So this is a limitation of relying on these neural reconstruction approaches for simulation. And finally, here we can apply some random sensor failures by blacking out a random subset of camera frames we're conditioned on, and we illegally drive in the middle yellow left turn lane for some time before deciding to drive back into our original lane. So obviously AlphaSim, this Gaussian splat simulator, enables us to characterize our policies under realistic perturbations, but it has limitations in that we can't really characterize how it works under other weather patterns or lighting patterns. This is where we can rely upon game engines like Carlo. Here we have a nighttime scenario. There's a pedestrian crossing the street, and thankfully our vehicle decides to stop safely before crossing the intersection. However, we can take a look at a morning, rainy, foggy scenario. In this instance, our reasoning says that there is a red light. However, our vehicle still decides to run the red light and actually almost, if not actually, hit our pedestrian on the street. So this is extremely unsafe, and yeah, I think Waymo, whoever, would actually get sued by using this policy. This is where we really want to be able to proactively characterize and understand our model under any given scenario. This requires asking questions like, how certain is my LLM policy? Should I trust the planner? Does it tend to predict any particular actions? And what if I were to change the prompt slightly? How does my policy change its predicted action distribution? And for the remainder of my talk, I'll be focusing in a simplified simulator which provides this top-down 2D highway environment driving scenario where we take observations from the simulator, convert it to text, and stress test these large language model policies. But I want to note that the same framework I'm about to present is directly applicable to the large vision language models we just saw. So we might have an observation from your environment which we convert into text. This includes your ego driver's observation, the observations of the other drivers on the road, your preferred driving style, as well as what discrete actions you can take in the real world. Here's an example of how GPT, a closed source model, acts in this environment, where your green vehicle is your ego policy, and the blue agents are your non-ego agents. In this case, we see that the policy acts pretty well without colliding into the other agents, while still maintaining a high speed. However, we can take a look at some other LLMs here, and we see that each of them act pretty differently. They act pretty erratically, even crashing into your other agents. We see examples of behaviors like rear-ending, performing pit maneuvers, or excessive switching, which are extremely unsafe and undesirable. And we can actually look at the closed-loop metrics of how each of these different policies act in your world. So we are characterizing DeepSeek, Llama, Dolphin, and Qwen, 4 different large language models, and seeing what is their predicted action distribution across several different seeds and across different time steps. We identify that each policy has a unique driving style. We see, for example, that DeepSeek is extremely conservative, whereas Llama acts more erratically. This leads us to say that proxy models are not an accurate indication of how other policies will act in your similar scenario. This is critical because there's several instances of hallucination intervention algorithms that rely on these proxy models, and we find that these aren't great in these decision-making tasks. We also analyze how our models react to manual prompt perturbations, like changing your preferred driving style, removing sensor data, or randomizing the order of details in your prompt, etc., and identifying how inconsistent these sampled actions are to understand uncertainty. This is just
sorry. Can I ask a quick question?
Yeah, of course. Yeah.
So I think initially you showed some videos from color and Gaussian splatting, but eventually the models you're evaluating are it seems like you're using just a text-based inputs, right? You're not using that image. So are those 2 different settings, or actually they are studying the same problem, or actually they're different?
Sure. The simulator is different between the this high fidelity simulator you see in this slide over here, and this simulator you see over here. They're 2 different simulators, and we're stress testing vision language models in the first scenario, and we're testing large language models in this other scenario. What I want to showcase here is that the current work that I've developed has been evaluated on these large language model policies, but there's in-progress work on applying this framework that I'm about to present to also vision language models as well. So the main difference is just one sense of modality. What I'll be showcasing is how we can actually perturb not only text, we can also perturb images to actually, and the scenario as well, to actually understand where these models fail. Does that answer your question?
Okay, so so in the second part, you input is it's just a purely text based, and you're like translating the language model output to this figure, right? So So the language model doesn't see this cars the positions,
Exactly,
relative
exactly,
positions
yeah.
between the cars and so on,
The
right?
language model will only see, it'll see this sort of information that includes the ego driver's
Okay.
statistics and the other vehicles and stuff like that. And the reason we
Okay.
did this is because there's existing works that utilize LLMs in this way. So Dailu is this work specifically is one example that really prompts LLMs in this manner.
That makes sense. But in the animations and figures you showed here, there seems to be like many cars in a similar environment, right? Do you tell large language models the location of every car? Or it also looks like the text only carries limited information, right? It probably doesn't
Exactly.
know if they change the lane whatever else in the other lane, right?
Right. I do feed the available information of all the different agents. So here's, for example, I hid these slides, but I can show them. So here's one example where we have an instance with only, sorry, I have to bring that slide back up. This is an instance where there's only one vehicle or a few vehicles in front of our policy. And we also stress test under other instances where there's many more vehicles around the object, around our ego vehicle. So we directly feed the available observation from the sensors in your simulator to text that's directly fed to your LLM. Does that answer your question?
Okay, sounds good. Thank you.
Yeah, thank you for the question. So what I was just saying is that we can measure the inconsistency of these different policies under manual prompt perturbations. This is an example of how DeepSeek will react to certain types of prompt perturbations where we see, for example, only providing lane information or providing a subset of your position details actually leads to high inconsistency from your policy. And obviously, as we add more information, our robot becomes much more certain of what sort of actions it wants to take. What I really want to do is to characterize our policy automatically without relying on this manual prompt perturbation definition. This requires asking questions like which scenario our model is likely to hallucinate in, which prompt perturbations impact our decisions the most, and how should we augment our prompt to get the LLM to act in a desired way. And this is where we rely upon adaptive stress testing. So as we go from this high-level instruction following scenario where we have knowledge about the individual modules in our pipeline into utilizing these black box large language model planners, we can see that utilizing adaptive stress testing enables us to find these failure modes from our policy. So AST is a tool we can rely upon to find worst case scenarios where your policy under test performs poorly. And we do this by relying on reinforcement learning. So you can think of AST as a translation of one-step adversarial attacks you might be familiar with within image classification to multi-step decision making, like airplane collision avoidance, for example. And AST consists of a simulator, which holds your model under test, as well as the environment that we're trying to stress test the policy in. And an adversary updates the simulator and receives rewards based on how poorly the model under test performs. And most importantly, we treat our MUT as a black box, meaning that we don't need its hidden weights nor its output token probabilities. AST has been used in different domains like airplane collision avoidance, autonomous driving, and most recently causing LLMs to generate undesirable text. However, what I want to note here is that this most recent work utilized AST in a gray box manner, whereas ours is black box. So what does it really take to use AST in our setting? Well, we need to model adversarial prompting as this Markov decision process built up of your state space of perturbation settings, your set of perturbation actions, state transition dynamics between these different states, and finally, a reward function for finding hallucinations. And I'll be walking through how we can define each of these four things. First off, we want to define our perturbation axes. The two I've formally defined is the first is rephrasing our prompt given the same semantic meaning. Intuitively, we should expect our policy should produce the same output over multiple samples if it's given the same semantic meaning prompt, if it's certain of what sort of action to take. And the other axis is evaluating our robustness to different sensor failure modes. And we should expect that our policy might actually produce other decisions under these failure modes. However, we want to ensure that the predicted actions are actually safe to take in your environment. Now, based on these perturbation axes, we can define our state space. we can freeze the highway environment to a particular scenario we want to stress test our policy in. And our AST simulator says, how does my original prompt perturb? This includes details on what is my preferred driving style, what is the available sensor data available to my policy, do I have few shot examples or add noise, etc. And based on these state space definition, we can define our action space such that we can choose to what our preferred driving style is, whether we remove sensor data or augment our prompt description. So we can visualize what a perturbation tree might look like as we build it up over time. For example, the first adversarial action our adversarial agent might take is to set the conservative prompt. We will utilize our prompt generator, which is hand engineered to generate n new prompts, which are fed to our LLM. These generations are cached and saved into a generation cache, which we can then compute the undesirability of. And I'll discuss in just a little bit how one can define undesirability. But what I want to show here is that the reward that our AST agent receives is the change in undesirability from the prior state, where the undesirability of your first state is 0. So intuitively, we're trying to find trajectories within this tree that lead to highly undesirable responses from your policy. We can define undesirability in several different ways. These are 3, where the normalized action diversity and the normalized Shannon entropy represent finding perturbations that increase uncertainty from your policy. And the negative average MUT reward here can be used to find perturbations that cause critical failures from your policy. For example, crashing into other vehicles or wrong way driving. And I want to showcase here that your engineer can design the undesirability function, however they choose to do so, to find the characteristics that they care about. So going back to our tree here, we can take another action, like removing velocity data, updating our prompt template, feeding it to our MUT, caching our responses, computing undesirability, and again, providing our reward to our adversarial agent. As we can see, this tree can grow quickly complex. And what I want to show here is that our generated prompts are grounded with these templates, making sure that they're not hallucinated. Our LLM is treated like a black box, so we don't need its hidden weights nor its output token probabilities. We as an engineer can define the undesirability metric to find characteristics that I care about. And by caching these actions predicted by your policy, you ensure determinism during this tree space. And finally, by defining our AST reward in this manner, we're finding these actions that result in decreased desirability from your policy. However, searching this entire perturbation space is extremely expensive. For example, in the highway environment, we have 240 different perturbation states. And for each of these states, we're going to sample from our model n different times. And for each, we might want to actually characterize m different scenarios. For example, build m different trees. So for just 20 different scenarios, and for 5 samples per state, we might need to actually sample 24,000 times from your policy. This is where we need to rely on an intelligent manner to search this tree space. Here we rely upon Monte Carlo tree search, where we can utilize this RL algorithm to find trajectories that lead to high expected undesirable states within your tree space. But I want to note that we could have relied on other, perhaps more sample efficient methods for performing this tree search. We saw that MCTS works well in earlier AST approaches, and it works well for us. And compared to related works, there are several gray box approaches like conformal prediction that rely on the confidence scores, whereas ours works on black box models. And there are several approaches that might only perturb a portion of your observation space, whereas ours perturbs the entire observation space for more informative insights. And finally, there's many approaches that actually generate hallucinated prompts, which will obviously lead to hallucinated generations, whereas ours are grounded in the observation space with these templates, ensuring that they're not hallucinated. And remember, these templates that I've discussed are hand engineered, but what I want to showcase here is that we could have relied upon agents to automatically build this perturbation space and write your code for your prompt generator. So what this might look like is, given our onboard sensors, we feed it to our agent, which then decides to generate your sensor and rephrasing perturbations, as well as your code for the prompt generator API, which is fed to your AST search algorithm. But this comes at a cost of potential hallucinations during the generation process of this perturbation space and the code for your API. So this is really a balance we need to strike between scalability of our algorithm, where we can't potentially rely on humans to create this perturbation space all the time, and also limiting the hallucinations generated for more informative insights.
So I have a quick question, just for clarification. for the AST, you generate a tree, right? But does the node on that tree, does the order of the nodes on that tree matters? Does that mean you add the first perturbation, the first time step, second perturbation, second time step, or you actually add all the perturbation eventually together to the prompt?
Yeah, we eventually add all the perturbations together. That means that multiple different ordered perturbations might lead to the same perturbation state.
Okay, but why using this kind of tree structure, right? So if the order doesn't really matter.
So this is one example of this tree structure where we do see that that there are no instances of where multiple trajectories lead to the same state, but this doesn't really matter to us. Like in the future visualizations I'll be showing for actual legibility, will be actually, we essentially treat our environment in this manner, but our algorithm doesn't need to know that it's not actually a tree where there's multiple trajectories leading to your same perturbation state.
But I mean, if there are multiple trajectories leading to the same perturbation, that means your search part of your search space is redundant, right? You don't have to, search that large space. So if you have more efficient representation of all the perturbations.
I agree, yeah. As I mentioned, we could have relied upon other sorts of representations and RL algorithms to search this sort of space. And like you said, there are redundancies within this tree space. But we actually visualized through different experiments that this tree space is still more efficient than random search baselines within this environment. Yeah, but I do agree that this could have been defined. We could have used more sample efficient approaches for this tree search.
Okay, sounds good. Thank you.
Yeah, thank you. Any other questions?
I have another clarification question as well. So since Juan mentioned time, right? I was wondering, so it seems like you basically only predict a single action, or what, but then you showed us these videos of how you basically predict this whole sort of trajectory, like how, what's the role of time in this?
Yeah, that's a good question.
I'm missing something here, I think.
Sure. We're choosing to characterize our policy in a particular perturbation state. So let me actually...
But it's like a current state of the environment.
Current state of the environment, right. So the actual time axis here is essentially not exactly time. It's essentially adding perturbations that cause
You're sort of sampling different states of the environment, right? But they're sort of very, so it's sort of like data augmentation or something, where you have like different variants of the current state. Right?
Yeah, like the underlying state of the environment is fixed. It's our observation that we're providing to the...
Yeah, get it. But then ultimately, the LLM has to predict the actions of your agent, right? Like say how the car drives or whatever, right? And like how many time steps do you let that run, or how important is it to let that run for?
So in this plot over here, let's say this is our current prompt template. We generate n different prompts. In our experiments, we choose to generate 5 variants using this prompt template and sample 5 times from your policy. So for each perturbation state, we sample, let's say, 5 different actions from the policy for that particular state.
Oh, so you sample 5 actions, say, in each state.
In each state.
I see. Okay. And then you evaluate where the system ends up.
Sorry, let me go back to this undesirability metric over here. So by utilizing the action from our policy, we can, for example, utilize this negative average MUT reward over here. This is an example where we utilize the action predicted from the policy, feed it into the underlying environment to see what the reward was from the underlying environment, which we feed as the undesirability metric to the policy, to our adversarial agent. The other ones above it, the normalized Shannon entropy and the normalized action diversity, compute the uncertainty of the policy under those 5 different actions sampled under that state condition.
Okay. So it's 5 different actions at one time step. It's not
5 different actions at one time step, correct.
Okay. But so you're just predicting one action.
Yeah, sorry, yeah.
Okay,
It's
that's
one
basically
action
what
sampled
that's
5
that's the
times.
time question that okay. Got it.
Yeah.
Okay. Thank you. Yeah.
Yeah, no, thank you. That's a great question. Yeah.
Yeah, so basically, I just want to clarify that better. So, for example, one action is remove velocity. That means you basically didn't tell the large language model velocity for the entire trajectory, right?
Correct.
Okay, sounds good.
Yeah. Awesome. Thank you. Sorry, let me go back to that slide. I think we were over here. Okay. Now we want to evaluate our algorithm, right? We evaluated and stress tested 3 different large language models across different capabilities, utilizing our 3 different undesirability functions, and we characterize a policy utilizing whole, deep, and shallow trees. So the whole tree searches your entire tree space, whereas deep and shallow trees search only 25% of the perturbation states. We also evaluate them in 3 different environments, including autonomous driving, robot crowd navigation, and moon landing. And we also apply them apply the characterizations online for 3 different applications. So first, we want to collect a set of scenarios. We want to stress test our policy, and so we let our LLMs drive on the road, and we choose, let's say, 20 different scenarios that we actually want to stress test our policy in. For each of these scenarios, we're going to feed it through our Monte Carlo tree search algorithm. And the next couple of slides, I'll be showing how we can characterize llama utilizing a shallow tree with the action diversity undesirability metric. So we can visualize, for example, what is our predicted action distribution over all perturbation states, over all sampled actions from our policy. In this case, we find that our policy is pretty uncertain between accelerate or decelerate, which is actually undesirable, because if it accelerates, it will crash into the vehicle right in front of it. We can also visualize our sample diversity over all the different perturbation states. And we find that each perturbation state has a different majority voted action, meaning it has a different decision mode it wants to take. And there's also instances of perturbation states with high uncertainty from our policy. We aim to understand what these perturbations were for further failure analysis. So we can easily do that with our graph search here. We have the top 3 and bottom 3 perturbation states that led to the most and lowest undesirable metrics. And I want to showcase here, even in the low diversity perturbation states here, we still had instances of different decision modes from our policy being predicted. We can also visualize what is our reward distribution over all these different adversarial actions. So for example, we find that removing acceleration data tends to lead to more uncertain states for this particular policy. And we can build a characterization data set over several different scenarios. And by doing so, we can visualize what is our uncertainty distribution of these policies. So for example, we can look at the predicted action distribution over all perturbation states, over all sampled actions, and compute the entropy of all the samples from all your perturbation states. This leads us to plot for each of the different scenarios, what is the sensitivity of our model under all the search perturbations. We can also visualize, for example, for the low diversity perturbation states, what is the entropy of the majority voted actions from this policy, enabling us to plot what is the distribution of these high confidence decision modes. And by plotting these 2 graphs, we can actually find what are the 2 scenarios on the 2 ends of our uncertainty characterization spectrum. So this is one instance on the left-hand side where our vehicle is obviously going to decelerate, whereas the policy on the right-hand side, it visualizes a blue agent merging into the lane to the right of it, and it is either going to merge left or decelerate. And we can actually perform this characterization over all of our different large language models over the 3 different characterization tree types. So here this plot showcases what is our Shannon entropy over all samples and our low diversity majority voted decision modes for each of the policies. And the first thing I want to showcase here is that our more capable models like Quen tend to hallucinate less frequently. They have a lower Shannon entropy. And as expected, these whole trees find more instances of unique decision modes. This is to be expected. Yeah.
Why does a model being more certain imply that it hallucinates less. It might just be
Yeah,
more
okay,
certain.
that's a great point. Yeah. Me as an engineer, let's say I define my undesirability function such that I want to find uncertain uncertain instances for my policy. I'm saying that this is an instance where my policy is hallucinating because over multiple samples, it's generating inconsistent responses for my policy. But I could have defined it in another manner. I could have defined my undesirability metric in a manner that says like utilizing the negative average MUT reward, for example, it could have led to crashes. That's another instance of a hallucination. So this is just one example of how I define hallucinations. Again, an engineer can define it however they choose to do so.
Yeah, I mean, like there are standard definitions, say in NLP for hallucinations, right? That have nothing to do necessarily with like how certain the model is.
That is correct.
But I just wouldn't call this hallucination probably.
I see.
Necessarily, it's it's just sort of certainty or uncertainty. But you can be very certain and very wrong, right?
That is correct. Yeah.
Right. But yeah, we can take this offline. But
yeah, sounds good. Yeah, that's a great point.
Thanks. Yeah.
Those are definitely some comments I had during the review process during my survey paper. People had differing values on what hallucinations were, but I totally agree. This is a conversation we can have. Yeah. Thank you for your question.
Yeah, let me also ask a quick question. So can you go a few slides back? You have a figure where the x-axis is the number of actions or something. I didn't quite understand.
Oh, sure, yeah. Like, is this plot?
Yeah. What does this mean?
So we have, for one perturbation state, we look at how many, sorry, where's my mouse? Oh, I see it. Okay, we look at how many unique actions were sampled from the policy under that perturbation state. And what this plot is showing is how many perturbation states on the y-axis led to how many different number of unique actions sampled from your policy over here. So this is where 4 is on your x-axis. These are all instances of perturbation states that had a 4 unique action sample from your policy.
Yeah, but there are more than 4 colors there, right? I just don't fully understand this.
I can explain that. So we sampled, again, remember, 5 different actions from the policy, right? Per perturbation state. This color is representing what is our majority voted action under that perturbation state. Yeah. So this is like, yeah, is that clear?
No, I'm still not very clear about this.
No, I think the confusion is so in the 3Ks, right? But you have a no strict mode, right? So presumably that means you don't have a majority, right?
You don't have a majority voted action.
But you have 3 possible actions, right? Idle, acceleration, and
oh no, there's
right?
merge left, there's merge right. Like these are the 5.
So what does number of unique actions mean in the x-axis? So is that so? What's the what are you varying for these 5 different conditions?
Right. The number of unique actions here is saying, let's say there's 2 left sampled, there's 2 right sampled, and 1 idle sample. There's 3 unique actions actually.
Oh, across. Okay, I see. Okay, that wasn't clear to me.
I see.
I was also assuming that you had somehow restricted the available actions or something, but that's
see.
Okay,
yeah.
Got it.
Yeah.
Okay, sounds good.
Okay. Cool.
Good. Thank you. Yeah.
Okay. Yeah. So we're back here. The final thing we can also see here is that while the whole trees find more instances of these unique decision modes, our partial trees, the shallow and deep trees, still meet the characterization standards of our whole trees in terms of what ratio of these searched perturbation states were actually found to be undesirable. And we can actually utilize these sorts of analysis at runtime to actually understand, engage with whenever our LLM is sensitive to any particular data, or hypothesize if it's certain in a particular case, or perturb your prompt to change your chance of hallucination or undesirability. So what this looks like is, given a new unseen scenario, we can look up in our characterization data set for the closest characterization, utilize our prompt generator to generate either undesirable or desirable prompts. And for the sake of time, I won't be going into these results, but I'd be happy to showcase them during any questions or anything like that. Now, what we really aim to do is to provide legible advice to the engineers who utilize our algorithm. What this means is, this interface over here enables engineers to load up a characterization tree that they've learned, and each node in this tree is a perturbation state where edges represent the individual adversarial action taken. Now, our engineer can choose to color each perturbation state according to their undesirability metric. So for example, they can color it based on the normalized Shannon entropy, or the normalized action diversity, or the negative average MUT reward, where each color here, red means more undesirable, whereas green is less undesirable. We can also color it based on the majority voted action. So here, this enables us to understand what were our actual decision modes under each perturbation state for our policy. And by clicking into each perturbation state, we can visualize what were the generated prompts given our perturbation state, what were the sample decisions from our policy, what were the rewards by actually taking these actions in the simulator, and etc. And finally, what I want to showcase here is that we can actually click into our reward distribution plot below and highlight edges of the individual. I hope you can see that. We can highlight different edges in our tree that represent the actual adversarial actions that led to these different reward distributions, providing the engineer legible understanding of where these failure modes arose from. So the main takeaways from this section of our talk is that foundation models can obviously hallucinate, or they might crash, they might provide undesirable generations. And we present this black box, this adaptive stress testing tool that is applicable to black box LLMs. And our analysis provided by this algorithm can be utilized at runtime, as well as for providing legible advice and for adversarial prompting. And this algorithm is applicable to any LLM, any environment, but it requires choosing a diverse set of coverage scenarios to actually evolve to new unseen scenarios at test time. And I'll talk about scalability in just a little bit. So this brings me to the conclusion of today's talk, where I want to bring it back to the beginning. I envision a future where humans are seamlessly assisted by real-world embodied agents. However, this future is a far cry away because of failures that can arise in your pipeline. And I argue that human input is crucial to mitigating these failures. In particular, this human input should be considered throughout the development and deployment process of your planner. And really, we need to consider the evolving robot capability and the human domain experience that they have to actually understand these failure modes from our policies. So we went from this low-level teleoperation scenario where we need a lot of domain experience to control our policy. We need to understand the inner workings of our model. And we went to this higher level instruction following scenario that has higher robot capability, while having different modules to enable us to identify root cause failure modes. And finally, when we're relying on large foundation model black box planners, we can rely upon black box AST approaches to actually stress test these policies and find these failure modes without having to have knowledge of what the inner workings of this model. And we've specifically developed tools to support real-time failure recovery, efficient adaptation to user data, finding failure modes, and discovering these undesirable behaviors. And I want to talk about the future of anomaly-aware human-robot teams, specifically focusing in the autonomous driving domain. So we can see several different robots out on the road today. We have Zoox, Waymo, Neuro, Tesla. There's millions of pedestrians out on the road today. There's other vehicles, there's semi-trucks, there's delivery robots. There's a lot of different human stakeholders in your pipeline. For example, the passengers in your car, the software engineers developing the tools, the teleoperators controlling your robot, and the policymakers who are holding these models accountable. And finally, the environment around us is changing rapidly. We have Waymo expanding out into London later this year. We have Tesla, other companies expanding across the US, and the sim-to-real gap we see in different high-fidelity simulators is quickly closing. What I argue is we need to develop scalable characterization algorithms for the future of anomaly-aware human-robot teams. That means relying upon real-world data where we can. So for example, this is one instance where a human accidentally actually trips in front of our Waymo, and our Waymo thankfully gets out of the way. This is an instance that our engineers may not have actually come up with during their stress testing pipeline. How do we combine real-world insights with simulated data while being constrained by the domain experience of real engineers, all fed to our automated discovery evaluation pipeline for actionable advice? This requires asking questions like, how can we combine insights from simulation and real-world data? How do we further close the sim-to-real gap? This is where we might be able to rely upon world foundation models, which offer high-fidelity sensor sources. How do we distinguish anomalous cases from out-of-distribution scenarios? This is critical as companies are expanding out into new environments like London. Everything is out of distribution. How do you know what is actually something we need to care about? This is where we can potentially rely upon the reasoning capabilities of large vision language models, where relying on a human may not be feasible at scale. However, this entire time we've been talking about how these models can hallucinate. This is where I really believe that human engineers are required to constrain our perturbation space and verify uncertain scenarios for hallucinations, relying on their domain experience. And finally, how can we leverage these insights from our characterization for downstream policy improvement, where really we want to avoid catastrophic forgetting of earlier learned skills? So if there were three main things I want you to take away today, they would be that human input is critical for mitigating failures. As we evolve the robot capabilities and the human roles in our human-robot teams, we need to develop adaptive solutions for these failure mode model characterizations. And finally, the future of HRTs requires developing scalable algorithms. And just on the first point here, human input is critical to mitigating failures. I need to thank several people without whose input I would have faced many more anomalies during my time here at Illinois. Of course, I need to thank Katie, who has been an amazing advisor. She's watched me grow since 2019. I really appreciate the collaborative environment that you fostered here in the HCA lab. I don't think I would have been able to work on these projects or really have the freedom to explore these ideas anywhere else. And I really appreciate how personable and supportive you have been, both professionally and personally throughout my entire time here. Speaking on that, I think the multi-agent RL survey I did earlier back then, I remember you actually sat down with me for a meeting that's like an hour and a half, just like me talking to you. And now I feel so bad for doing that, but I really appreciate all the feedback you gave me throughout my years here, so thank you. Thank you to Julia for being my advisor on the SimBot competition. Thank you for welcoming me into the team, even though I started late. And really, that project was so exciting because I was able to tackle a project at a scale I've never experienced before. So thank you for your input and advice and for helping me out throughout the years. And thank you to Melchior for being on my, and collaborating with me on my hallucination survey and the AST work. You've provided invaluable advice throughout each of these works, without which I don't think these works would get accepted at anytime soon. So I really appreciate that. I also appreciate the random funny comments you put on my papers. Like I would create a figure with really tiny text, and you say, "No God on earth could actually read this." So that really made my day. Thank you to Juan for all of your questions and for all of your advice and for being on my defense committee. And thank you to Lav for being on my prelim committee and for all of his input as well. Of course, I need to thank my parents, without whom I would not be here today. They've been with me every step of the way. They've even actually gone to conferences and with me. And I really appreciate all the support. You've always said and told me to explore the directions that I'm excited about, and I really appreciate that freedom that you've given me, so thank you. Thank you to my extended family across the world. This includes my cousins, my aunts, my uncles, my grandparents across the entire world. I hope to see you all again, and I'm very thankful for all the support you've given me throughout these years. And to even my family friends in Nashville, they've always welcomed me in as families and treated me with high hospitality every time I've been there, so thank you. Of course, I need to thank the lab. I believe if I hadn't had you all as friends, I would have gone insane much earlier in my PhD. Thank you to Katie for hosting all these parties at her place, and to Yeji and Andre for organizing different social events, whether they're dinners or escape rooms or hiking, including other events. I really appreciate all the fun moments we have and the memories I'll never forget. And I also appreciate how much you put up with me for being in the office and talking too much. Thank you for being there with me. And thank you to the Simba team. When we weren't locked in that Siebel room, we also had a lot of great moments inside and out, so I really appreciate you being there. Thanks, Hao Miao, for the heart. And of course, thank you to all the friends I've made along the way here. I came to Illinois in 2017, having known absolutely no one. And I'm very fortunate and grateful to have made as many friends as I have throughout the years. And whether that was karaoke nights at Murphy's, or playing Super Smash Bros. In undergrad apartment, or going hiking, or all the dinners we've had, thank you for always being there. And yeah, I think a lot of us will be in the Bay Area again, so we'll definitely have to keep that up. And finally, thank you to all of my collaborators, without whom none of this work would be possible. And I'd like to give a special shout out to Shui Jing, who was my mentor, my first ever mentor in undergrad. She brought me in and really fostered me into the researcher I am today. So thank you, Shui Jing. And with that, I'd love to take any questions at this time. Yep. Thank you.